So far, we've learned about how to determine if a function is continuous and the different types of discontinuous functions. Now we're going to talk about the properties that continuous functions have. So theorem 6 talks about f and g, which are continuous functions at a point C, then the following combinations are continuous: the sums of the functions, the difference of functions, the product of functions, if you multiply that function by a constant, and if you divide two functions as long as the denominator does not equal 0. So these properties are very similar to limit properties. Theorem 7, however, is a little bit different and might seem a little confusing. If f is continuous at C, which is again any x value, and g is continuous at f of C, then the composite g of f is continuous at that point C. So if a function is continuous at a point, and then you take a composite of it, which is putting a function inside of another function, the composite function is also continuous. So we're going to look at an example right now where we have f of x is equal to sine of x, and g of x is equal to x squared, and we're going to want to show that the composite function sine of x squared is continuous. So the first step to do this is to identify the composite function. So sine of x squared is equal to f of g of x, because g of x is x squared. So if we have f of x squared, we get the function sine of x squared back. So in order to show it's continuous, all we have to do is show that it's a composite function and each part is continuous. So since sine of x squared is equal to f of g of x, where f of x is equal to sine of x, and g of x is equal to x squared, and f of x is continuous and g of x is continuous, then f of g of x, which is equal to sine of x squared, is continuous. So it's important to note that these are my conditions, and then this is my conclusion. So let's try another example. In example 4, I want you to try to show that y is equal to the absolute value of x divided by x squared plus 2 is continuous. So the first step to doing this is we're going to determine the composite function that makes it up. So we need to determine what is the outside function. And so I see we have an absolute value that surrounds the entire function. So I'm going to say f of x is equal to the absolute value of x. And g of x, then my inside function, is going to be x divided by x squared plus 2. So this is the outside. And this is the inside function. So just looking here now, we have that the outside function is the absolute value of x, which we know is continuous. And the inside function is a rational function, which is sometimes discontinuous. However, the way to make a rational function discontinuous is to set the denominator equal to 0. Well, because we have x squared plus 2, x squared plus 2 can never equal 0. So now all we have to do is write our conclusion. So since f of x is equal to the absolute value of x, which is continuous, and g of x is equal to x divided by x squared plus 2, which is continuous for all x, and f of g of x is equal to the absolute value of x divided by x squared plus 2, then f of g of x is continuous since f of g of x is a composite function. There's a couple different ways you can word this that slightly rearrange the order that the conclusion is in, but as long as you have all the parts, it's going to be fine. So now on your own, I want you to try to show that f of x is equal to the square root of x divided by x plus 1 is continuous. All right, let's give it a try. So the first thing we need to do is break this down into two smaller functions. So I'm going to say that f of x is going to be equal to g of h of x. And so g of x is going to be my outside function, which I notice is the square root of x, because you can see the square root is holding all the rest of the function inside of it. And my inside function is going to be x divided by x plus 1. So now all we need to do is show that each piece is continuous. So we get that, so since g of x is equal to the square root of x, which is continuous, and h of x is equal to x divided by x plus 1, which is continuous, and f of x is equal to the composite function g of h of x, so then g of h of x is continuous, so therefore f of x must also be continuous. So a side note to make that's very important is that a function is continuous even if it has a point of discontinuity, as long as the point of discontinuity is not in the domain.